current slide.
Yes.
Okay, yeah. So this is Pradip Majumdar. First of all, I'd like to thank you, the organizer, for this conference, for inviting me to be a speaker. Just wanted to say a few things about what I've been doing. Currently, my work is involving around this dealing with multiple AI-oriented kind of work. We work on multi-physics computation, AI machine learning application, and IoT edge devices. Some of the product lines are dealing with battery design software that includes AI integrated algorithms. So one of the things is the BESA AI, which is some of the work you'll see today in my presentation, is relates to that kind of work that we have been doing there. Here is a glimpse of that, what we do here. If you have a requirement to design a battery, lithium-ion battery for EV or any other electrification needs, you might have a target performance and structural needs, and you can specify in terms of voltage, capacity, weight, and ranges. So our algorithm basically trying to use databases, take the constants, take the material data for the batteries and performance data from vendors, a wide range of data we try to use, and we try to use different layer of modeling, including multi-physics modeling, most part of it, but then we want to go into AI type of algorithm to pinpoint our design and operating conditions there. So with that background, let me start with what we, just to give you a few glimpse of what we think, what I think in terms of this very important topic that really affecting many areas, right? So artificial AI is a broader field there, and it basically refers to a model that performs tasks emulating the way human intelligence is doing that, and more specifically tries to perform the tasks and cognitive functions the human does with a subjective and also intuitive manner. A subset of this AI thing is the machine learning, right? And that basically tries to extract the patterns and concept in a and builds up the knowledge and try to refine that without really explicitly programming it. And tries to use big data volumes in order to really achieve its goal. Next layer is the deep learning, and which is a subset of machine learning. This is a little bit more advanced than the machine learning in the sense that this relies more using the architectural and neural network, and it tries to minimal manual intervention in terms of understanding the concept and the features. It does a lot of automation involved in that one. And finally, the latest trend that is going on, latest advancement that is taking place on top of that deep learning machine learning is a generative AI, which is really built on around that deep learning architecture. So let's start with I think in the predictive analysis that people are using and we are using for using machine learning. And basically what we are doing is that we always refer to this kind of detection algorithm as a trained algorithm there that will try to watch for the patterns on incoming data set so that we can target its values that you're trying to look for or look for any kind of anomalies that is there. In this figure that later on you see some kind of example that I have in dealing with this application of this algorithm for detecting the engine combustion. I think we'll show you that one. But mainly what is required is this one for this purpose, using the big data analytic techniques, which you look for the pattern there. And data could be historical data, large volume of historical data. It could be also new data that we are streaming. That can be also used. Can detect the pattern and try to learn to make the prediction and recommendation. Some of the things that we'll be doing in terms of learning and improving the prediction through iteration, we call this one in machine learning as approaches. Using the new set of data is basically will be try to refine the model, and this particular stage we call the learning process. Here's a typical machine learning model that people like to build, and we have been working on this. This is the way it is. So you start with you can start with some kind of a data set that you have, large data set that you have, that you can use it, and you can use that to build this model, right? We call the train model, and over here. So that's how you select the model, you select the algorithm, and you train the model using all the data there. Once you have the trained model, then you further test it, validate that one with another set of data that you know is correct, And once it is validated, then only you can deploy that. Either you can use it for your prediction through use of a edge device or some kind of a with some kind of embedded machine learning model that you embed then the edge device and try to predict something there. And at the same time, you try to collect new data sets. So you continuously feeding that one, and with a period of time, you try to retrain your model, and that's the loop you would do that. That is the basic machine learning model that we normally use it. So, and you can see that it is becoming extremely popular among many areas, including robotics, bioengineering, health monitoring, and that involves any kind of a IoT-based kind of a predictive operation. And basically all these cases, you need to build this application. You need to have your own historical data and also real-time streaming if you like to do some kind of predictive analysis model. Just to give you a glimpse of this one, what we are doing in the first basic machine learning model that you'll see is dealing with the statistical analysis kind of thing. Let me see if I just move my screen. Can you see my screen? Sorry. Okay, let me see. Okay, something happened to my screen. Yeah, sorry, I'm back. I'm back with that. Let me see if I can share that again. Something went wrong. Can you see now? Hello? 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 Can you see my screen? Sorry. Hello? Hello? Hello?
Yes, I can see your screen.
Oh, okay, okay. So, but do you see my slides?
No, I am seeing the Zoom screen.
Oh, what happened? I don't know. Let me just try to reshare it. Okay, that way. How about now?
Yes.
Okay. Okay, sorry, something happened there. So I just wanted to share with you on this slide a basic example. We did it with the machine learning, and that is mainly one of the algorithm based on the multi-variable regression kind of things. And we try to do it for the case of a battery cell performance data, and basically in a battery, there are a lot of different kind of a feature, different kind of variable parameter. Over here, we try to use it, there are three of them. One of them is the temperature of the operation of the battery, and also the current density that will indicate the rate at which the battery is basically discharging the power to the EVs. And we are trying to watch it for the cell voltage, temperature, the time, and the current density there. So in order to really predict that one over here, we try to use this method with right now we are using two variables, x1 and x2, and the objective is to predict the voltage there. And you see, we use a huge set of data for that one. And if we just apply the machine learning based on regression, you'll finally come to a equation that is mainly operation of linear metrics evaluation. So you try to find out, represent the function relations given over here, y as a function of c's. And if you get the c values done, then you should be able to use that function relation to predict that. So, and it basically it went down to an operation of figuring out the matrices, and w over here is the weighting factor or tensor, you can call it, and the function f of that is basically the function that retains all the data points, coming out of the data set that you have there. So with this particular one, we found out that if you see this, that the blue dots are the actual data points, and the red lines are really falling on that one is the actual predicted function that is predicting this range of operation up to about 800 seconds. This is a case with a very fast discharge of the battery with a rate like about 3C rate, but it is doing a very good job in terms of RMSEs and R2 values there. Okay. And then I think let me just move on to the next slide. And So if you look into the why now machine learning is becoming more popular, because there's a lot of advancements took place in the machine learning algorithm, not just one algorithm over a period of last 20, 30 years. A lot of breakthrough took place. We have a technology of digitalization of many things, and you have a very available, very large set of data for whatever specific application that you're looking for. And also rise of cloud computing and huge computing power, that is there, that's primarily taking advantage of the GPU chips there. And there is also taking place a lot of machine learning algorithms, but especially the one that is dealing with the neural networks, right? That basically identifies the feature and understand the concept there. So that neural network that is being used now, and there's a lot of open source platform that is built around that, are like TensorFlow and PyTorch. So availability of those, along with the availability of the huge computing power, making people like us and many other people has the opportunity to use this one. If I just give you some basics of what is there in terms of the machine learning techniques in dealing with the deep learning there. It is a deep learning is another extension of machine learning which uses multiple hundreds or more, multi-layer hidden layers, and it is using a large number of neurons and synapses in a multiple layer, so that, and it can also take in a wide range of unstructured data. It could be text, images, and signals, and try to predict generate certain things and predict certain values of that one. One of the things, example for this application of deep learning, people have been using it for the last 10 years over there, is to learn the features in large complex data set. But in step by step, they figure out the feature. Example is trying to figure out the particular shape type of a car in an image, like when you try to stream the data from the cameras of a car, and from there you try to figure out that. So that's what it is. It does. Next layer of this machine learning to deep learning is the generative AI, which is we are talking about. This is another layer, another advancements of the deep learning. It's basically not only try to identify the pattern from last set of data, but it can also generate new content. Like it can generate video, it can generate images, and it can generate programming code and translate the languages. So people are now rushing towards because of these capabilities. This kind of generative AI is really built around the large neural network foundation models, such as the large language model, LLM, and it is using billions of neurons, millions of deep layers to and try to use a multiple billions of parameters probably is fitting in to interpret data and generating this. But I think this is also very extremely computing power wise is extremely expensive. Only few people, few organizations can even try to train that over a period of maybe 10 years, to train this kind of model. And we refer to this kind of very advanced training model as foundation models. And some of them, all is the one that is ChatGPT, OpenAI, Dell also by OpenAI, and also Gemini by Google. This is some of the advanced foundation model that is already there. But now I think why people, as not all companies can develop this or train these models. We have to rely on this one, but it can be, this kind of model can be customized, so long for your application. For like our application, we try to use our own historical data sets that we have been having it. It could be manufacturing operating process data. It could be technical reports, sensor their data, and it could be case studies. Anything can be, we can create our own database and customize our application model based on this kind of a foundation model. Last layer is the artificial general intelligence, AGI, which is it is much closer to the human cognitive functions, operations such as reasoning, problem solving, perception, learning, and language comprehension. So it is doing multiple things, not just one operation pattern. This is I think decades away, but is also coming in future probably. So, and in terms of generative AI model, there are different types of model will be available, and based on which one our application is related to select on that. It's a wide field of that. Of course, the first one is large language model, as you can see that is being used for generate. It's trying to process generate natural language text. So some of these chatbots are developed based on that particular kind of model. Next layer is the generative adversarial network (GAN), which is mainly used for generating new images, audios. People are being using that and trying to using is a new areas of creating deep fakes and anti-deepfakes, like the way we cybersecurity figuring out the viruses, antiviruses. Same way, this kind of areas are basically built around this particular network, GAN network. Other models that is quite often used for creating the chatbots, a transform-based model that tries to learn the context using natural language processing tasks like machine translation, answering the question, or image recognition. And the last one I listed over here is the variational auto encoder model, which is very similar to GAN. It transforms large set of data and compresses into smaller representation and used to generate images, videos, and audios values. A quick look at this network. What is the neural network includes. It is inspired by the biological human brain, actually. That's right. So named following the computational model of the biological system. Deep learning method uses ANN, artificial neural networks, and a type of machine learning algorithm under the umbrella of artificial intelligence, and builds to understand the complex concept. Some of the neural network architecture that we see in the literature, people are using it, is feed-forward neural nets, convolutional neural nets, recurrent nets, long short-term memory (LSTM) nets, autoencoder representation learning model. Each one of them is itself is a very complex architecture and algorithm, a mathematical representation. In this particular, the one we are going to focus a little bit more, which is related to our time series prediction, is it can be used as a convolutional neural networks net. So let's look into that. What is that one? So CNN, convolutional neural network, is basically a specialized form of network that uses data in grid-like format, like you see in a two-dimensional time series data, or a two-dimensional image data with pixels. Primarily used for predictive analysis in a time series stream data from IoT sensor for computer vision or processing images that are represented by a huge number of pixels there. The network and the algorithm search identify and try to learn some features of that image or time series and try to get a lot of details in a piece by piece manner. CNN apply basically one of the things you have to is different than the other ML algorithm is that CNN basically applies a new mathematical operation called convolution, which is in contrast to the matrix multiplication that you've seen before in the machine learning, that based on the regression kind of approach, statistical approach. Convolution is applied to at least one of the layer of neural network. So here is a typically the way the convolutional neural network was built based on many years of research and breakthroughs. Primarily, has been used for the computer vision processing images that are represented by millions of pixels. This is a deep learning algorithm. Researchers identifies and learn major feature, but on an item from large number of images. So you take large number of images, and then from step by step, you try to figure out the finer elements and then more details. If you can see that why it was built, people, the researcher that developed this over a period of 20-30 years, who is going around figuring out what's really going on in the human brain. And in the human brain, there's a multiple layer in terms of figuring out the images there. So the first layer is the receptors or detector field that try to identify the shapes or the color. Next layer, this is fed to the neurons, which is corresponding to the different respective field, and then the data is stored in the outer layer of the brain, which is called neocortex regions. That stores that process data. With that understanding, people try to develop CNN architecture, where they try to use the multiple layer, which could be hundreds of millions of layers, and they try to break this down into lower filter, where with the probability distribution, and they try to figure out some kind of a feature, high level feature in that particular layer, and then it's followed by multiple high level filter similar to neural context. So lower layer filter would ask a specific feature with highest probabilities, and then the mid layer, higher layer will detect more complex feature based on output from the lower layer, and then highest layer will identify the image. That's the concept that they try to follow as much as they can. Here's the convolution and a little bit of math on that one. What is convolution is doing? We have a in this particular expression that you see on the right hand side operation, the x is the unknown dependent variable that you like to find out as a function of the dependent variable, let's say t there. But you'd like to use you'd like to represent the x, which is you are looking for. You'd like to convolute that one on a different frame, which is y. Okay, which is basically x is weighted with that y, and your objective is to that w is a kernel. It's like a tensor to kind of stop with the distribution that you like to minimize so that your prediction is correct. So that's the and this is the integral of that one. That's the convolution definition. But in terms of programming, we like to discretize that one in a discrete form. That's what is summation of that. And you can change it the way the first equation that you see is only one independent variable, but you can expand that to multiple variable like the one you see later on with the I and J, representation. So that is the main concept of programming that one. But along with that, there's another concept built in CNN. It's called the pooling function. And the purpose of the pooling function is to replace output of the neural net at a certain location. So if the image there, you have multiple millions of pixels, but you like to focus on smaller area region and let you resolve that one. With highest probability, you can say this for certain, this is this, so that piece by piece you can have the confidence in predicting the rest of the feature of the image there. So in a typical convolution neural network, you will see that 3 stages. The first stage is basically at least you have to apply convolution, that mathematical operation, to at least one of the layer of the neural network, followed by multiple activation function type of activities in the rest of the layer, and then finally you have to do the pooling a function in order to figure out resolving each feature in different region of the image that you're dealing with. I think I'm not sure how much time we have, but let's move forward with this one. Typically, in network, you'll see the 2 main features. One is the tensor and the graphs. Tensor basically is a data type, so it's hold the multi-dimensional array of data in that one. It holds the inputs and the targeted output values. It manipulates all the model parameters. Basically, this tensor, that's why the name is tensor, is particularly suitable to GPUs to accelerate the computation there. And the graph basically will show the actual operation in different layer, how these features are identified and progress towards the output that you're looking for. So that's the graph structure there. So that has got it has got a nested kind of each layer. If you see that each layer will have a function that is the time to resolve the input value that's coming from the left hand side with the weights and the biases that is given. You tend to refine that one to another functional representation and moving towards the right where the output is. So you have this neural network, you have the 3 things: input layer, hidden layer, and output layer there. You can see that the edges are the hidden layer, and it is always getting some values not only coming from the input layer, but also getting its weights and the biases. But it also tries to does its own operation and try to refine these weights and biases there and go towards the output values. Some of the major parameters that is in neural network that is involved if you're trying to do if I try to do this deep learning kind of algorithm, it's input output layer, hidden layer. You have a number of neurons that can be varied, number of neurons or number of type of neurons, and then synapses, activation functions, learning rate, and finally the optimizer that tries to optimize the rate at which you're resolving the weights and biases coming from each layer and moving forward. Here is the activation function expression that you'll see. There's wide varieties of activation functions applied in each layer. That equation that you see is that is applied with a weight and WK and a VK. And job is the objective function is to resolve what values to be selected before you proceed to the next layer of that one. That's what it is. And then finally, learning rate will tell how fast the weights and the biases are updated on that. And then the thing that you're trying to optimize, the cost function for machine learning deep learning, is one of the cost function is root mean square error, or MSE, that you try to minimize that with respect to these parameters of the predict parameters of the weights and the biases there. So that's what you tend to optimize that. And the last feature of that one is the optimizer, as I mentioned to you. The optimizer basically is one of the optimizer is the gradient descent. Many people are used that one in optimization study, but here is also used it in trying to see the basically algorithm tracks the gradient of the error function with respect to parameters like the how it is really changing and what direction is going. Is it going in the direction of descending gradient? That's why it basically selects that one. So that is a very important piece of the deep learning that you try to use it in order to control, and you can vary that one with the hyperparameters like learning rate and the step sizes. I like to quickly show you our some of the features that you try to use this one in predicting the lithium-ion battery storage application. What is the data we used it for historical data that we generated based on multiphysics modeling. You can see that basically these are some of the time series data that is showing you each line of this that you see a different color. These are different kind of a C rate or rate at which the power is dissipated to the car or the battery pack is dissipating the energy. And faster the rate you do it, C rate, faster the battery is going to drain down. And it's basically on the axis over here is the time or could be current density. As you can see that it starts with the peak value of the voltage, slowly it goes down. And it's a signature. People who can look at the signature itself, you should be able to figure out how good the battery pack is doing. And you can see that in the database that we created with the different types of chemistry, including lithium iron phosphate, NMCs, number of cells for each time, the operation, the discharge charge, C rate, to mention the environmental temperature, time, and then we watch out for the current density and the cell voltage. So and all the multiphysics historical data that you generated is in terms of, let's say, temperature and the concentration distribution. You use that one to basically train the model. So this is becoming our historical data set that we collect the data and we try to train the model, we try to validate that, and we try to hope, and purpose is to really not only for predictive analysis in our design, but also put this in edge device for the BMS system monitoring the battery performance, so that you can make sure that we are trying to staying close to the peak performance that you can have. If there is any kind of a anomalies, that should be able to correct that one. Maybe the cooling system to be corrected, cooling flow rate should be corrected so that you can stay in the right place. Here's another regenerative. I think we mentioned that in my title, that I think one of the huge case of the CNN and the promise for deep learning and CNN architecture is the design of engineering devices. One of the key one I see that people are using, also already using it, is the design of the wind turbine. So on this particular screen that you see that over a period of 7-8 years, we have been performing this design of wind turbine. We're using computational fluid dynamics, and in that particular case, not only you're trying to see the maximum torque or the power output that you can get, but also you're trying to making sure that the error question noise is low frequency band noise is also low. So you solve both the computational fluid dynamics and also error acoustic equation, and you can see in the image that it shows us basically the pressure distribution around that, and also similar image you'll see where the low frequency noises are generated, how it is dissipating that one. On this particular figure, it tells you the selection of the blade, and it tries to tell you exactly how the boundary layer is separating and creating might cause the problem of the noise and also lower than the performance of that one. And so we try to do extensive, but thing if you like to do this one on a try to resolve your design based on just the multiphysics computational fluid dynamics is extremely manual workflow. First of all, even if you use the state-of-the-art software, it is computationally a number of grid is like a 2 million grids are there, and it is very small type step because it's transient. Large set of data are operating parameter, and so it's very hard to only just one few design iteration itself, it takes weeks and months. So I think this is a very different approach where we can look into it, is that we can generate certainly the data, but we can also try to take advantage of this the CNN deep learning algorithm, where you can we can take into account all the features like geographical location, wind speed, aerodynamic design of the blade itself, so we can modify that, and we can look at the wind speed and the weather data, and you can take out the manufacturer wind turbine performance data. That data might be generated by CFD, but also you can use the data from some of the wind turbine manufacturer, use that one. And then based on that, and we can take into account of the design constant, and that will help us to really figuring out all combination of parameter, and really are looking at millions of variation in the design, and that narrow down the design that is best for that particular location and that particular application, that one. So, but I think we need to, in order to do that, we need to perform extensive amount of collection of the data that we need. So what here you can see that for this particular operation of the generative design, we need to look into a multiple aerofoil blade design, rotor size, rotor height, wind speed, 5 to 2.5 meter per second, blade rotation rate, all kind of variable you can take it and you can generate the data, or you can collect the data from the manufacturer, which is already being done for different region, and you can run that. And you can see that when you create this one, the data for aerodynamics will give you this pressure distribution around the blades, and try to tell you how much is the lift you're getting it, which is contributed towards the creating the torque or the power of that. Here's the weather pattern that you can real-time capture it. It is all there, and we can take that data and try to select. This is Illinois in USA, and we can select which region which is most suitable, and we can select the region, and based on that, we can say that the design will be based on that particular region. Here is again the actual power distribution and the pressure distribution that you get around that, which will contribute to the power. So here, I think some of the data that we have been collecting for this particular application, not only the CFD generated data for the pressure coming out from physics, but you can see that some of the manufacturer data are over here that you can use it, and that gives you the power wind turbine power output based on different wind speed and blade angles. And this is some of the variation of lift forces generated by the CFD. This historical database, along with performance data, might it can fit to the deep learning CNN model to pin down the multiple data. And finally, I think if you give a few minutes, I think I'd like to speak about this deep learning AI technique for that we used it for predictive analysis of internal combustion engine. And the challenges over there, you can see that another thing we like to resolve is the time of ignition and rate of duration of combustion, because this particular thing impact the performance production of the species, in particularly NOx formation and other things. And we like to resolve that one involving multiple parameters that involve intake temperature, air fuel mixture, fuel types, equivalent ratio, engine cooling system, and parameters there. So that is the challenge. But to do that on a high fidelity software, and you can see this one that we have been using this one with a compression fluid dynamics approach, but that requires a huge amount of time. Each of the run that you need to do to figure out what kind of NOx is forming, what is the time of duration. It is. I think some of this run we took about a day or two to do that. The reason for that, you can see that we can solve the equation for physics, but then we have to look into the kinetics to see what kind of species will form there, and from there I think and figure that, and then determine the based on that we figure out how much heat is generated, what the temperature pressure peaks are, and based on that we can feed that to chemical model again and figure out what kind of species forming and temperature pressure values, and then you advance the time. So it's a very rigorous process of that. So we decided to go into this. We already have the data, but now we can't resolve the find. We can continue to use the CFD model to generate more data there. But we like to we have been developing this AI machine learning based design analysis for the predictive analysis. So this is dealing with the deep learning neural network, and you try to use the historical data that is coming from the high fidelity software CFD models. Here's a concept. You see that basically you can take a physical model of the engine, define all your input performance parameters and variables, and we perform this 3D high fidelity simulation, which requires a solution of maybe a Stokes equation, turbulence model, chemical kinetics evaluation is unsteady, and then you figure out the heat dissipation and temperature distribution there. So basically, it is generating millions of data over 1.5 million grid points that you have there. So use that one. And this is a sample data that you can see that shows the how the during the run of the engine, crank angle, temperature, pressure, and the number of moles of species formation that is taking place, temperature that is peaking out. I can see that on this figure. This is the start point of the ignition, and duration is kind of for a short duration. Actual combustion is taking place, and the whole focus is around that, because this is going to control the temperature and how fast it is. It will control whatever performance that you're trying to achieve, the losses and the NOx formation of that one. So we take this kind of data and we feed that into neural network. And in this particular case, the figure that you're seeing, it got used about 5 feature input over here: RPM, compression ratio, intake temperature, equivalent ratio, wall temperature, and it tries to vary the number of inner layer, and trying to look for output is basically you're looking for the start time and end time. So while training the model, we got the values of start time, end time, and we used about 40,000 values for creating the model. That we have 40,000 data point. We used it for training it, and then we used another 30,000 data to validate that one. So here's some typical data sample that you'll see that we fed in to create about close to 100,000 data points was used to train, validate, and evaluate the network. And at the end, I think you can just to show you a sample. What you do, watch it is this is showing you one hidden layer and 10 neurons, and you try to modify your input layer activation function, which is called sigmoid there, and you can also use 10 hyperbolic for the inner layer activation functions. Over there, you can use about 10 neurons there, and then finally we can also use hard sigmoid in the output layer. And it's basically we try to watch out at what rate or approaches this training your error is coming down. Both the training and the validation is coming down, and we noticed about how much, about 10,000 iteration, 100,000 actually, coming down to a level, acceptable level. It's kind of a highly iterative, highly fluctuating values, but eventually it's coming down to the value that you're looking for. And we did enough number of cases that you tried, and you can look at that error level over there in terms of RMS values. And here's another sample of that one. In this case, we use probably much more number of hidden layer, but the number of neuron in each layer we jumped up to 10 times more, and you see a better values, better results coming out of that. And we can we can compare this number of layer as you go up on this one, and you can try to see continuously how improvement we made in terms of our prediction there. So with that, I think I'd like to conclude my talk. I think my time is up. I'm sure I'm took a little bit more time than I was given, but thank you very much for listening to me. Any question?